And now for our final class of functions, which will Lebesgue integrate. Section 4.4 is called a general Lebesgue integral. So the class of functions we're considering, class 3 functions, my terminology, is those functions which may not be non-negative, may not be bounded in the sense of the class 1 functions we considered, but we're still imposing a certain type of boundedness on these. Our big concern now is infinity minus infinity popping up in some of the definitions. So what's totally driving class 3 of functions is avoidance of that. We're allowing unboundedness, so infinity can definitely pop up. We're not restricting ourselves to non-negative, so subtraction's on the table as well. That's meaningless, so that'll have to be avoided. First, we'll take an extended real valued function f on set E and define the positive part of f to be the maximum of f of x and 0, and the negative part of f to be the maximum of negative x and 0. So when x is positive, the maximum of these two is f of x itself. When x is negative, the maximum of these two is 0. When x is 0, they're the same. So what we've basically done in defining this f super plus, this positive part of f, is we've gone along and chopped off all the negative values. If you like, we've rounded them to 0 in creating the positive part. The negative part's similar, but oddly enough, the negative part is also non-negative. The negative part of f is defined as the maximum of negative f of x and 0. So when f of x itself is negative, then the maximum of these two is negative f of x, which is, in fact, positive in that case. When f of x itself is positive, well, if f of x is positive, then negative f of x is negative, and the maximum of those two is 0. So what we're doing here is kind of twofold. If you like, we're cutting off all the positive part, maybe rounding that down to 0, and then introducing a negative sign and flipping it over about the x-axis, so that the positive part of a function is positive, the negative is, well, non-negative, and the negative part of a function is non-negative. So that's the definition, and there's good reason to do it that way. We know how to integrate non-negative functions. So that's the real reason they're defining positive and negative part the way they are. It seems the negative part should be negative, but this is how they're defining it, giving us the relationships that the function itself is the positive part minus the negative part. This we'll see again when we're dealing with linear combinations. And if I add the positive and negative part, we actually get the absolute value of the function. And we'll see some of that again as well. We know from the previous section how to integrate class 2 functions. And we had defined a non-negative function to be integrable, provided the integral of that function was finite. So what we're going to consider in this section is integrable functions on a set E. And this will ultimately accomplish the avoidance of the infinity minus infinity arithmetic that could definitely appear, especially if we just mindlessly try to write the integral of function f as the integral of the positive part minus the integral of the negative part. Those could well both be infinite, and we got a problem. So we're avoiding that. The next result relates the integrability of the non-negative functions, positive part of f, negative part of f, and the absolute value of f, and says, for a measurable function f on set E, the positive part of f and the negative part of f are integrable over E if and only if the absolute value of f is integrable over E. That is, the integrals are finite. For proof, to the supplements. Okay, let's prove that. Several of the proofs are not too hard in this section. We've got a pretty good amount of theory behind us. So we've got a lot of equipment to use in this section. For a proof, it's a if and only if. So suppose the positive and negative parts are integrable over E. That means the integral of the positive part over E is finite, and the integral of the negative part of f over E is finite. And again, positive and negative parts are themselves non-negative functions. The positive and negative parts themselves are class 2 functions, as I've introduced that terminology. So all this stuff with the integrals is previously defined, including the integral of the absolute value. I mean, that's a non-negative function as well. We have linearity for non-negative functions. We've expressed previously the absolute value of f as the positive part of f plus the negative part of f. Well, that's an integral of a linear combination. Theorem 410 says integral of the linear combination is a linear combination of the integrals. And Theorem 410 said that for class 2 functions, for non-negative functions. Okay, well, that's what we've got in this particular computation. Linearity gives us this. We know, or we've hypothesized here, that the positive part is integrable and the negative part is integrable. That is, this and this are both finite, so their sum is finite. And so the integral of the absolute value of f is finite. That is, the absolute value of f is integrable, in the sense that that term was introduced at the end of the last section, meaning the integral is finite. So if positive and negative parts are integrable, then so is the absolute value. Let's reverse that implication. Suppose the absolute value of f is integrable. That is, the integral is finite. Now, all this conversation is taking place in this setting of the previous section, class 2 functions. We know that the positive part of f is bounded below by 0 and above by the absolute value of f. Negative part of f bounded below by 0 and above by absolute value of f. Remember, it's non-negative. Well, we've got monotonicity of integration for non-negative functions, what I call class 2 functions. You've got monotonicity. Okay, bigger functions have bigger integrals, crudely put. So we get the integral of the positive part is less than or equal to the integral of the absolute value. And similarly for the negative part, by the way, we got these bounded below by 0. And the integral, we're assuming now, of the absolute value is finite. So the integral of the positive part is finite and the integral of the negative part is finite. And both positive and negative parts are integrable in the sense that the integral is finite. So now we're going to define the definition of integrable, previously dealt with for non-negative functions. We're going to extend that definition to this setting of general measurable functions. So a measurable function f on set E is said to be integrable over E, provided the absolute value of f is integrable over E. In that case, define the integral of f over E to be integral of f over E is the integral of the positive part minus the integral of the negative part. Okay, well, everything in sight is finite with this integrable hypothesis, as we just saw. If the absolute value is integrable, then the positive and negative parts are integrable, so no infinities here, and it makes sense to take a difference of those two. And that's totally how you ought to be computing these integrals, just with the foresight that we better be careful about divergence and infinity minus infinities. And class 3 of functions will be these functions which are integrable. So this is our final class of functions. So what we'll be doing in the remainder of this section pretty much is establishing properties of integrable functions like linearity and monotonicity and a convergence theorem, and additivity will pop up as well. The previous results this proposition 414 about absolute value of f is integrable if and only if positive and negative parts are integrable. Then we see that integrable f implies that both the integral of the positive and negative parts are finite. So as I stated, we've avoided the infinity minus infinity stuff. That's what's totally driven our very definition of integrable. And our class 3 of functions are these measurable functions which are integrable over a given set. So for some properties of class 3 functions, of course, these are going to look rather familiar. We can throw away sets of measure 0, is what proposition 415 says. Let f be integrable over E. Then f is finite almost everywhere on E. And the integral over E of f equals the integral over E set minus E sub 0 of f, provided E sub 0 is a measure 0 subset of E. So we can throw away sets of measure 0. A proof of that, not very complicated. We'll just translate it into class 2 functions, into non-negative functions. The absolute value of f is finite almost everywhere on E, provided we have integrability of the absolute value, proposition 413, from the previous section. If we had a finite integral, we had a function that was finite almost everywhere. So applying the definition of f is integrable to mean the integral of the absolute value is finite, and deducing from that in proposition 413 that the absolute value function is finite almost everywhere. So f itself is finite almost everywhere. As claimed, f is finite almost everywhere was part of the claim. Now for the integral claim, the integral over E of f is the integral over E of the positive part minus the integral over E of the negative part. That's the very definition of the integral of functions in class 3, integrable functions. Now, you can throw away a set of measure 0 if you have non-negative functions. That was part of additivity of the integral, Theorem 411, when we were dealing with non-negative functions. As I said, let's take it from this class 3 function to these two class 2 functions, these non-negative functions. We had the result there. So throw away that set of measure 0. You'll get equality of the integrals from the fact that these are non-negative functions, Theorem 411, back to class 2. And now we're integrating over a set, a positive part minus an integral over the same set, negative part, well, by the definition of integral of the function f over that set, it is the difference of these two. So by definition of integral, we can glue these back together to get the integral over E set minus E sub 0 of f, and that was the claim. So cute little argument where you take the question from this class to the previous class using a definition, have the property there in class 2, bring it back to this class using the definition again. So pretty straightforward stuff so far in this section. Next result kind of reminds me of the direct comparison test from Calculus 2. It dealt with the convergence of improper integrals. You'd be given an improper integral and asked not to evaluate it, but be asked, does it converge or diverge? And this was dealt with, I think, always for non-negative functions in that setting, I think it was. And the idea was to directly compare the given function to a function you can integrate. We'd bound that function above, and if the function bounded above has a finite integral, then the lesser function has a finite integral. So I think it was dealt with non-negative functions. Or find a function less than or equal to the given function that you can integrate and see if that integral diverges to infinity. Then the bigger function must have an integral that diverges to infinity. The trick was to introduce a new function that compared favorably to the given function that you knew how to integrate. So this is rather similar to that. There's a link to some calculus notes, calculus 2 notes that describe that. But it's similar in that we're bounding a given function by a function of known behavior. Let f be a measurable function on set E. the integral comparison test it's called, says if there's a non-negative function g that's integrable, okay, so there's the real constraint. So we've got a function g that's integrable, that is, the integral of its absolute value is finite, and the absolute value of f is less than or equal to g on set E, then f is integrable over E, and the absolute value of the integral is less than or equal to the integral of the absolute value of f. Okay, so what we're doing is dominating this function f by a function g in this sense, where the function g is integrable. We don't have monotonicity. We don't have monotonicity for class 3 functions. We do have it for class 2 functions. But when I say dominating, I mean something about an inequality. We'll have some kind of domination when we have our convergence theorem. It's called the Lebesgue dominated convergence theorem at the end of this section. Why all this domination boundedness stuff? Yeah, I'm worried about infinity minus infinity, as is the driving force throughout this section. So let's look at a proof of the integral comparison test. Okay, again, hypotheses. There exists a function g that is integrable over E as a finite integral. And we've got this inequality here. By the way, that implies g itself must be a non-negative function, given the inequality on set E. Okay. Monotonicity of integration. Yeah, we've got that for non-negative functions. The absolute value of f is a non-negative function. G is a non-negative function because of the inequality, as just stated. And we know the integral of this function is finite. You were told g is integrable. Well, if this function, a non-negative function, has a finite integral, and this function, a non-negative function, is less than or equal to this, then the integral of the absolute value of this must also be finite. Compare smaller to bigger functions, lesser to greater functions. They have lesser integrals compared to greater integrals. Provided we have monotonicity, we do. Both of these functions are non-negative functions. They're class 2 functions. So we had monotonicity. I guess it was Theorem 410 that gave us the monotonicity in that class of functions. So we get that the integral of the absolute value, that must be finite. In other words, f itself is an integrable function. Okay. Let's deal with this absolute value of the integral. All right, and this is end of proof down here. This is a quick argument as well. And it's simply a matter of taking the question elsewhere. Let's take the integral over e of f to, by definition, integral over e of the positive part minus integral over e of the negative part. Okay, this time we're actually going back to the real numbers as a familiar place. This is some real number. The function's integrable, so this is finite. Some real number. This is some real number. We got the absolute value of the difference of two real numbers. Triangle inequality tells you that's less than or equal to the absolute value of the first plus the absolute value of the second. Oh, by the way, the positive part's a non-negative function, so the integral is non-negative. The negative part is a non-negative function, so the integral is non-negative. So I don't need absolute values around these two integrals, though we did have the difference turn into a sum when we applied the triangle inequality. All right. Now we've simply got the integral over e of the positive part plus the integral over e of the negative part. I can use linearity, right? Right. These are non-negative functions, and we have linearity for non-negative functions, right? The positive and negative parts, they're class 2 functions. Theorem 4.10 gave us a linearity for those. So we can use linearity from Theorem 4.10 to write these as the integral of the sum of the positive and negative parts. And the positive part plus the negative part, remember, was the absolute value. So that's just a substitution there. So definition, triangle inequality from the reals. linearity from class 2. So we went back to the reals for some inequalities, and we went back to class 2 when dealing with the positive and negative parts to paste them together. And then a definition that the absolute value was the positive part plus the negative part. So integral comparison test, I'd say there's a very reasonable result. Some of these things come off as fairly abstract. This makes pretty good sense. You do this kind of thing in Calculus 2. It's quite similar to the Calculus 2 type results. Okay, purpose of the next definition. So typo there, thought I had corrected that. Here we go. Purpose of the next definition is to deal with a case of extended real valued functions where the value of the function could give a positive, an infinity minus infinity. We might have f taking on the value infinity, and we might have g taking on the value negative infinity. We're allowing these extended real numbers. So this definition will allow us to deal with those kind of functions by permitting this behavior, but restricting it to behavior on a set of measure 0. And we will ignore that set of measure 0. That's what the definition is going to tell us to do. So let f and g be extended real valued functions defined on set E, and suppose they are finite almost everywhere on set E. Say f and g are finite on set A, a subset of E, where the complement of A with respect to E has measure 0. Then we're defining the integral of f plus g over set E to be the integral of f plus g over set A. We threw out E set minus A. It had measure 0, and what we're doing is we're burying the extended real valued stuff on those sets. So we're requiring, when we do this type of summation, that f and g be finite almost everywhere. So we can take all of the infinity extended real valued parts, the infinity values for f and g, throw them into a bad set. And the complement of that set is set A, the good set. So they're in a bad set, and that set has measure 0 because of the almost everywhere part. So a little technical detail to allow us to deal with really throwing away sets of measure 0, even when we deal with extended real valued functions and there's negatives floating around. All right, so now we're ready for linearity and monotonicity for class 3 of functions, the integrable functions. We're ready for additivity, and we'll gear up for a convergence theorem as well. Linearity and monotonicity, our final linearity and monotonicity, because our final class of functions, third and final linearity and monotonicity result. F and G, this time hypotheses, are integrable over E, because that's what class 3 of functions is. Alpha and beta, last section they had to be non-negative because we could only deal with non-negative functions in the last section. None of that this time. So any alpha and beta, scalars, real numbers. The claim is the sum, alpha f plus beta g, the linear combination, is also integrable, and the value of the integral is what you think it should be. The integral of the linear combination is a linear combination of the integrals, and when f is less than or equal to g, the integral of f is less than or equal to the integral of g. So linearity, monotonicity, just like before. Maybe a little extra caveat here to comment that we are always dealing with class 3 functions here. The integrability claim is part of the story as well. Okay, let's look at the scalar multiplication first. All right, we're going to look at positive and negative parts. So whether that scalar is positive or negative will affect how we address those. Suppose alpha, the scalar, is positive or non-negative. Then alpha f, positive part, is simply alpha times the positive part of f. Alpha f, negative part, is simply alpha times the negative part of f. Straightforward. When alpha is negative, All the signs are going to change in alpha f. So the positive part of alpha f will be negative alpha times the negative part of f. Does that make sense? First off, this really is non-negative, right? Right. The negative part of f, ironically, is non-negative, and negative alpha is non-negative because alpha is less than 0. And similarly, negative part of alpha f is negative alpha positive part of f. So the alpha being negative reverses all the signs. So when we take a negative part of alpha f, it's related to a positive part of f. And similarly over here, when we take a positive part of f, well, a positive part of alpha f, the alpha's changed all the signs. And that's the reason you get a negative part of f out over here. Okay, so we'll have to consider scalar multiplication in these two cases, straightforward in the first one and similar in the second one, except there's some negative signs that are part of the story when alpha itself is negative. Okay, for alpha greater than 0, alpha f is, by definition, alpha f being itself an integrable function over set E, will be positive part of alpha f minus negative part of alpha f. The integral of such a function is, by definition, the difference of the positive part and negative part, I guess I should say. Alpha f is, by definition, this, and the integral of this, by definition, is the difference of these two integrals. We can rewrite the positive and negative parts in the obvious way this time, and a not so obvious way next time. It'll be this second way here with the negatives. We can bring constants out front. We're dealing now with non-negative functions, and linearity says, Theorem 410, for class 2 functions, for non-negative functions, you can bring the constants out front. All right. Factor the alpha out. That leaves us with this difference here. And that difference, integral of the positive part minus integral of the negative part, is the integral itself for an integrable function f. All right, so definition of integral, and through that procedure, we got the integral of alpha f equals alpha integral of f. The constant came outside. Now, when the constant's negative, well, it's quite similar. If alpha is less than 0, we start the same way. We use a definition to express it as a difference of two integrals. We substitute, okay, this time, when we took the positive part, we got a negative alpha and a negative part of f. When we took the negative part, we got a negative alpha and a positive part of f. Okay, so there's your extra negatives. Also, things are interchanged here, and good thing they are. We can bring the negative alphas out front if you like. Scalars come out as before, dealing with non-negative functions here. Also, the scalar's non-negative, right? Alpha was less than 0, so negative alpha is greater than 0. We didn't formally address alpha equals 0 in the proof, but it's not a surprise with the alpha equals 0. Both sides of the equation are 0, and we're good. Here, we factor the negative alphas out. We're dealing with non-negative functions. We're okay with the linearity from the previous section. Let's pull alpha out of that. We'll leave the negative sign here. You've got two negatives here to give you a positive. And there again is the integral of the positive part minus the integral of the negative part. By definition, that's the integral of the f function. Okay, that takes care of the scalars part. For the what I'd call the vector addition part, for the addition of the functions, we need to still establish that the integral of f plus g is the integral of f plus the integral of g. Quick little observation. Claiming absolute value of f plus the absolute value of g. This is integrable over E. Let's see, f was integrable. which means the integral of absolute value of f is finite. G was integrable, hypotheses, which means the integral of the absolute value of g is finite. So when I add those two together, linearity tells us the integral of the sums of these two is also finite, equals the sum of the integrals, which is finite. So that's why linearity is part of the story. And again, these are class 2 functions, non-negative functions. So we have absolute value of f plus absolute value of g is integrable over e. Okay, so we're looking for some integrability here as well. We've then got the absolute value of f plus g is less than or equal to the absolute value of f plus the absolute value of g. That's triangle inequality applied pointwise to, the triangle inequality for real numbers applied pointwise to these functions on E. So you can plug all them x's in there and say for x and E if you like. That's just the triangle inequality for real numbers. So the integral comparison test that allows us to talk about integrals, and it's the integral of this thing we want to talk about. We know the absolute value of the integral of f plus g we had shown was less than or equal to the integral of the absolute value. It was part of that integral comparison test. We're claiming that's less than or equal to this stuff here. What is that exactly? Is it monotonicity? Yeah, okay. These are non-negative functions, so I can use monotonicity if you like. So we can say the integral of absolute value of f plus g is less than or equal to the integral of the absolute value of f plus the absolute value of g, and then use linearity on that to get this. And both of these were finite, so we've got this integral is finite. So in particular, f plus g is integrable over e, as we claim. Proposition 415 said we've got integrable functions if and only if those functions are finite almost everywhere. So we must have f plus g finite almost everywhere on E. That is, f is finite almost everywhere and g is finite almost everywhere on E. We've seen by theorem and by definition, we can ignore sets of measure 0. So without loss of generality, we'll take f and g to be finite throughout set E. Throw away the set of measure 0 where you may be getting the infinities out. All right. Let's look at the positive part of f plus g minus the negative part of f plus g, because we want to integrate f plus g, and we'll have to do it in positive and negative parts. All right, well, the positive part of a function minus the negative part of a function is that function. So that little difference there equals the function f plus g. F, by definition, is positive part of f minus negative part of f, and g is positive part of g minus negative part of g. So we peeled this apart in a very, very clear, I think, and straightforward way. And we didn't jump from here to positive parts of f and g. So we went through this intermediate, but we're led to this equality here. So we can take the positive part of f plus g here, move that to the other side of the equation, and bring the negative part of f and the negative part of g to this side of the equation. So we get positive part of f plus g from here, plus negative part of f, negative part of g. Here's the negative part of f and the negative part of g. Take them to the other side of the equation. Okay, that's how they got to be positive. And now move this thing to the right-hand part of the equation. It becomes positive, and we're still left with the positive part of f and the positive part of g, arithmetic. So we've got this string of equalities. Okay, each of these functions, notice I got plus signs in front of them. So everything we're dealing with here is a non-negative function. So we've got positive functions all over the place, non-negative functions all over the place. And we've got linearity when we're dealing with non-negative functions because that's class 2. Oops. So let's integrate both sides of this equation. We'll have the integral of this plus the integral of this plus the integral of this using the linearity from class 2, Theorem 4.10, we've used over and over again. Integral to the left-hand side is this, and And by the way, all of these are finite numbers. Integral of the right-hand side produces these three integrals. Again, everything's finite. All these integrals are finite by the integrability hypotheses. So we can do subtraction, right? You be careful with that subtraction unless you know you're dealing with finite quantities when you're doing this extended real number stuff. So we can rearrange things with no concerns about infinity minus infinity. Everything here is finite. So let's see. Let's take the negative parts and put them with negative signs. So I'll take this to the other side and it will become a negative. Take these two things to the right-hand side. They'll become negatives. So I've written it down backwards here, interchanging left and right-hand sides. But we've got the integral of the positive part of f minus, when I bring it over, the integral of the negative part. Integral of the positive part of g minus the integral of the negative part. That's exactly what's given here. And we'll have the integral of the positive part of f plus g minus the integral of the negative part of f plus g, producing this last line. These two guys form the integral over e of f. These two form the integral over e of g. And these two form the integral over e of f plus g. And we got equality, and that's what linearity claims. So there's your linearity result for class 3 functions, for integrable functions, leaving us only with monotonicity to finish this result. So for monotonicity, again, f and g can be taken to be finite everywhere without loss of generality by throwing out a set of measure 0, either by definition or by theory from what we've done in the past. Okay, so define H to be G minus F on set E. We had set this up. I don't have the statement in front of me, but we had F less than or equal to G on set E. So this is a non-negative function here. We've avoided the infinity minus infinity because we've done the finite everywhere without loss of generality. We're integrating a non-negative function. They have integrals which are themselves non-negative. Linearity of integration holds for integrable functions. That's what we did in part A. So if we look at the integral of g minus the integral of f, that's the integral of g minus f. So there's the linearity part that we have now established for integrable functions. G minus f, that's a non-negative function. First off, I guess secondly, we define that to be function h, so this is a substitution. Now we're integrating a non-negative function. So you could compare the h function to the 0 function if you like, and use monotonicity. That's how it's intended to be applied here. And the integral of a non-negative function, of course, is greater than or equal to 0, but strictly speaking, I can get that out of monotonicity. I can probably dig it out of the definitions as well. And so take the integral of e over e of f to the right-hand side, and you'll get the claim. Integral over e of f is less than or equal to integral over e of g. And there's your monotonicity result for class 3. For integrable functions. Next up, additivity for class 3. Usual. Let f be integrable over e. That is, let f be a class 3 function. Suppose a and b are disjoint measurable subsets of e. Then the integral over the disjoint union of a and b, disjoint, is the integral over a of f plus the integral over b of f. You want a cheap generalization of this? Okay, a and b don't have to be disjoint. They have to be what's sometimes called essentially disjoint. They could overlap in a set of measure 0. Right? I can cheaply throw sets of measure 0 around and that doesn't change things. But here's the statement, why complicate things, that we have disjoint a and b. Proof of that. All right, let's introduce characteristic functions, as we often did. If we take the absolute value of f times a characteristic function on set A, that's less than or equal to the absolute value of f, all the characteristic function does is it on set A, it keeps the f values the same. Offset A, it makes this left-hand side 0, which is certainly less than or equal to the absolute value of f. And similarly, f times the characteristic function on B is less than or equal to the absolute value of f. All right. Then we can use the integral comparison test. This function here, absolute value of f, that's integrable. Right? F is integrable, and that's what f is integrable means. We can take the measurable functions f times the characteristic function of A and f times the characteristic function of B and deduce that they are integrable. The integral of the absolute values, integral comparison test. You could also use monotonicity. I could use monotonicity from the previous section, I think. But we've got this covered one way or the other. The integral over E of this must be finite because the integral over E of the absolute value of f is finite because f is integrable. And similarly over here. So both of these are integrable in the sense that their integrals are finite. Since A and B are disjoint, this is how we dealt with additivity the previous two times as well. F times the characteristic function on A union B is f times the characteristic function on A plus f times the characteristic function on B. The disjointness, of course, means you don't add the same two function values together for a given input value because of this disjointness. So if x is in A, you get f of x here, and you get 0 here, and you get f of x here. If x is in B, similar behavior. If x is in neither of those, both sides are 0. And there are no x's in both of them, by the way, because they're disjoint. Okay, so we get this algebraic relationship. What you think we're going to do next? Linearity, because we've got linearity here. Exercise 4.28 allowed us to conclude that 4.28, I guess maybe this is a new one. Yeah, because we're dealing with function f here. If we integrate an integrable function, f, and we've stated something about expressing integrals over sets using characteristic functions before, and that was a previous section, so that was non-negative functions. So this exercise must deal explicitly with integrable functions. But it can be shown in that exercise that the integral over set C of f is the integral over E of f times the characteristic function on set C, C being a measurable subset of set E. So we can take this equality, integrate both sides, the integral on the left-hand side by this observation, this exercise 4.28 is this. The integral of the right-hand side is the integral of a sum, which is the sum of the integrals, because we have linearity now. The integral of the first is this, and the integral of the second is that by exercise 4.28, and there's your equality. Additivity for class 3 of functions. And finally, for a convergence theorem for class 3 functions. So I say we impose a sort of uniform boundedness on a sequence of functions, f sub n, that will converge pointwise to some function f. Sort of. We dealt with uniform boundedness back when we had bounded functions. Here, I'm not worried about having unbounded functions. I'm worried about having functions with infinite integrals. So the sort of boundedness is more of a boundedness in terms of inflicting integrability on each of the f sub n's as well as the limit function. So this sort of uniform boundedness is accomplished by bounding or dominating the functions f sub n, not by a constant like we did in class 1 functions, but by an integrable function as follows. So I emphasize the word dominating because this is commonly called the Lebesgue dominated convergence theorem. That domination is done in terms of some kind of inequality. So let f sub n be a sequence of measurable functions on set E. Suppose here comes the hypothesis, there is a function g integrable over E that dominates f sub n in the sense that the absolute value of f sub n is less than or equal to g throughout set E. If we have the pointwise convergence almost everywhere on set E, then f is integrable, the limit function is integrable, and the limit of the integrals is the integral of the limits. Again, and one last time, because this is our last convergence theorem. The book leaves this middle part out. They just say the limit of the integral is the integral of the f function. But the important idea is, well, the f function, it's the limit of the sequence of functions. So you see the limit jump inside the integral. It's implied by what they have, but I want to make it a little more explicit. All right, so we've got domination by this function g. That must give us the finiteness to make sure you stay with integrable functions throughout this stuff. So any convergence theorem for any of the classes has to deal exclusively with functions in that class. We've had the bounded convergence theorem. We had the monotone convergence theorem for the non-negative functions, and now the Lebesgue dominated convergence theorem. And if we look at some of this Vitali stuff that's in a couple of the sections, then we might see another type of convergence theorem. And there's a generalization of the Lebesgue dominated convergence theorem we'll mention here shortly, but let's go through the proof of this. Okay. We've hypothesized the absolute value of f sub n is less than or equal to g on this set, and that we get the pointwise convergence of the f sub n's to function f, well, almost everywhere on set E. So it must be that the limit function also is less than or equal to g almost everywhere on set E. Apply this bound pointwise, if you like, almost everywhere pointwise. So we're stuck with an almost everywhere, but that doesn't affect anything. These sets of measure 0. Since g is integrable over E by the integral comparison test, we've got this bound. This is finite when integrated. So this is finite when integrated. And this is finite when integrated, integral comparison test. So f and all of the f sub n's, they are also integrable over E. They didn't impose that directly, right? They don't say the f sub n's are integrable. They don't say the limit function f is integrable. It's implied, and it's implied not very hard by the fact that you've got the domination by integrable function g. But notice that f and the f sub n's, they're all integrable. All right. Proposition 415, I forget exactly what that says, but we can assume we've got finiteness throughout. If we have the infiniteness, then it's going to occur on a set of measure 0. That's what proposition 415 said. If this function, say f, is integrable, then this function f is finite almost everywhere. So a set of measure 0 pops up where this function and the f sub n's may not be finite, and we can throw all those points away because that simply involves a set of measure 0, and sets of measure 0 don't affect any of these integrals. So we can remove those sets from all of those integrals. So functions g minus f and g minus f sub n that we're about to consider, these are properly defined. Well-defined is a term, similar term that algebraists tend to use. That is, you're avoiding the infinity minus infinity stuff because we're avoiding the infinity stuff. We got functions that are finite everywhere without loss of generality because we threw that set of measure 0 where these kind of things could happen. We threw it away, and we can do that either by theory or by one of the definitions when we were dealing with sums of functions. So g minus f sub n converges pointwise almost everywhere, so we still have that almost everywhere floating around, to function g minus f. All right, so we're going to consider this sequence. G minus f sub n converges almost everywhere to g minus f. We're going to apply first Fatu's lemma to it. Fatu's lemma would say the integral of the limit function g minus f is less than or equal to the lim-nth of the integrals of the, I want to call them the f sub n's, these things here. These are the functions in the sequence that we're talking about here. So we get integral over e of g minus f is less than or equal to the lim inf of the integral over e of the g minus f sub n's. We don't want no inequalities and we don't want no limits. We want limits and equalities for a convergence theorem. I think we're probably halfway there though. Okay. From that result, which is these terms here, we can take the integral over e of g minus the integral over e of f. F and g are integrable, g by hypothesis, f by implication. So we can use our linearity result for integrable functions, Theorem 417. It says integral of the difference, difference of the integrals is integral of the differences. Just do the obvious thing with the integrals there. It was Fatu's lemma that gave us this. Let's take that limit inside. We can deal with this as a lim inf of an integral of g. That's a constant, so as n changes, lim inf as n changes. It is a constant, so that's not affected. Plus, we'd get the lim inf of the integral of negative f sub n. Bring that negative outside, but that reverses inequalities. You've effectively multiplied by negative inside by doing that. And all lim infs then become lim sups. So by bringing the negative outside, the lim inf has become a lim sup. It's kind of manipulation you ought to see in senior level analysis. And we've got, let's see, the integral of g minus the integral over e of f is less than or equal to integral over e of g minus lim sup. I guess we could cancel those integrals of g, and we'd be left with, let's get rid of this negative sign on both sides too. We'd be left with the integral over e of f is greater than or equal to, when I multiply both sides by negative, lim sup of the integral over e of f sub n. Yeah, this little statement here. Eliminate the integrals over e of g. They're just numbers. They're finite numbers. Can't believe I have to say finite numbers, but with the extended real numbered stuff in the background, these are actual real numbers. So just subtract this number from both sides and then multiply through by negative. And that produces this. Very similarly, if we consider the sequence g plus f sub n, we go through similar type manipulations, and what you'd find would be you'd get the integral over e of f is less than or equal to the lim inf of the integral over e of the f sub n's. It would be quite similar to this. You'd be adding, and you wouldn't have the negative signs. So we'd end up without the lim sup, you'd keep the lim inf that Fatu gives you, and you'd cancel the integrals of the g's, and there would be addition here. And we'd do the same stuff, you know, with the linearity and so forth. And gluing those two results together, we get the lim sup of the integral of the f sub n is less than or equal to the integral over e of f, which in turn is less than or equal to the lim inf of the integral over e of the f sub n. Well, a lim sup can't be less than or equal to the lim inf. It can at worst be equal to it. So we must have an equality here. And lim sup, lim inf are equal. That establishes that the limit exists, that this limit here exists. We had lim inf. Oops, here we go. We had a lim sup of it here. We had a lim inf of it. It looks like down there. Those are equal, so that limit does exist, and its common value is the integral over e of f. So there's your convergence theorem. Our final convergence theorem of the standard ones, at least. And we can generalize that a little bit. The following, the generalization of the Lebesgue dominated convergence theorem. What it does is it replaces that single integrable function g with a sequence of integrable functions g sub n. This is to be dealt with in one of the problems in this section. Let's see, the g sub n's, I'll take it back. The g sub n's don't have to be integrable. They have to have an integrable limit. Let's see what it says. The general Lebesgue dominated convergence theorem simply weakens a hypothesis from a specific function to a sequence of functions with some appropriate properties. Let f sub n be a sequence of measurable functions on g that converges pointwise almost everywhere on E2f. Okay. No comments about integrability yet. Suppose there's a sequence G sub n of non-negative measurable functions on E that converges pointwise almost everywhere on E to G and dominates F sub n on E in the sense that the absolute value of F sub n is less than or equal to G sub n. Okay, so we've replaced the single G function with these G sub n's. And I still hadn't seen an integrability condition, but it's coming. If the limit as n approaches infinity of the integral over E of the G sub n's equals the integral over E of G, which is finite. All right, so there's your condition of integrability. It had to be somewhere in there. Then the limit of the integral of the F sub n's is equal to the integral of the limit of the F sub n's. You can take that limit inside. Of course, this is a generalization in the sense that we could just take all these G sub n's to be function G. And if you have this kind of behavior, that's the regular old Lebesgue dominated convergence theorem. So simply a slight generalization of it. And with that, we've completed our development of Lebesgue integration. So we'll summarize this in one of the future sections, but we've gone through 4 classes of functions. Class 0, simple functions. Class 1, bounded functions on sets of finite measure. No talk of divergence there, because there, everything was bounded that we computed with. Class 2 was non-negative functions. Okay, no concerns over infinity minus infinity. But we could have integrals be infinite. That can happen for Riemann integrals. You can get infinities out for values of integrals. So that could happen when we were dealing with the class 2 functions, but no subtraction, nothing was negative. So no infinity minus infinity concerns. And finally, this class 3 of integrable functions. And that condition of integrable is what allowed us to avoid any infinities minus infinities. We could have in this section some infinite stuff, but not infinite integrals. We did still allow the functions to take on extended real numbered values. So the function values could be infinite. But you read through the fine print there, that only happened on sets of measure 0 and all of this stuff. Okay, that takes care of our development of Lebesgue integration. We'll look at a few more little topics. I think there's a section or 2 left in this chapter, and chapter 5 that has some fairly brief sections in it. So we'll do that next. I will see you there. Have a nice day.